All right, so does anybody have any questions on the last material? Okay. So the last couple of main concepts we're going to cover are branch prediction, and we already covered cache coherence and cache consistency, right? So this is the last main topic we're going to cover. So up until this point, we dealt with ILP, we've dealt with some thread level parallelism, and we talked about simultaneous multi-threading, and we have these single issues or multiple issues of data, and but the whole time we have to worry about. And now we're doing this concept of in order issue, out of order execution, right? And so what happens is if you're running the code in different order, well, sometimes you're going to get to a point where you have to make a branch decision. If I equals j, I does not equal j, where you might not have the value of I or j yet, but you want to keep the performance going. So what happens is we're going to do this concept called branch prediction, where we're going to use the hardware, and we're going to study one particular method called 2-bit branch prediction. We're going to use hysteresis, and what hysteresis is it takes the previous branches and uses it as a way to determine whether or not we're going to take the next one. So if you've taken the branch, meaning that you've actually branched before, you're more than likely going to take the next branch as well. So if you branch not taking, you're going to not take it. If you go through the loop 100 times and you're not taking the branch, that means you keep looping through. And so therefore, that allows you to make that proper prediction. And what's going to happen is you do the execution, and if you realize you finally get that value of j that you wanted, and you realize, oh wait, my prediction was wrong, then you just undo all the executions using these reservation stations. And we're going to show you how to do this. So we formally define branch prediction as a digital circuit that attempts to guess the result of a branch instruction before the instruction is executed and required information for the branch is known. So before we have this branch prediction, we'd have to wait on both values to be able to get through there. So what happens is if it's a few stages behind the pipe, you'd have to start inserting more and more stalls, which then slows down the performance of your multiprocessor. The branch predictor avoids this waste of time by trying to guess whether the conditional jump is most likely to be taken or not taken. So it's using probability, and we'll go over this idea of hysteresis in a moment. And if the guess is wrong, it just goes backwards. It discards the executed result. So what happens is, think about it with registers. You have registers that have the updated values, right? That's what we've done everything so far. That's what you're working on in your projects. So you actually have another set of registers if you're in the middle of a predicted branch where you're doing your updated values and you store your original values. And if you find out that your prediction was incorrect, well, you just put the old values back in. And so here's a simple example. So we have I just equals L. I don't know why I said I instead of J there. So this is I. If I equals L, J plus plus, and then K plus equals J. So what's going to happen here is we're going to do a branch not equal. We're going to compare I and L. And in this case, I have S1 and S5. And I would jump to instructions, right? So trying to get to this point where K plus equals J. Well, what happens here is, let's say I have this value is going to be updated. Therefore, if this value is updated, if we don't take the branch, and we go in, then this value of j will be different than if we do take the branch. So this prediction becomes important in maintaining cache coherency because we have to maintain a copy of the cache value of j. So what happens is we were talking about distributed multiprocessors before, right? So we have the multiprocessor and it had its own cache, right? And then it had its own data memory, and then we had this kind of distributed bus for each one, right? So if I have a copy of j over here in this cache, and I have a copy of j over here, and this code is being run here, but before I should say L. We have L instead of j. I have to wait on L to be updated here before I know and push along the bus and put along there. So what is, first of all, before we go into branch prediction, what are the two mechanisms that we learned last class that do this, that take a look at all the different copies of the variables. Snoopy bus, and the Snoopy bus uses directory-based protocols. Yeah, so it's looking it all up and then snoops on there. So, but as the Snoopy bus is trying to get it from here to here, right? We have to make some sort of decision. So if we predict that the branch is not taken, that means we execute J++. So we've incremented J by 1. And then we would do the next instruction. If we find out that our updated value of L is not equal to I, that means we should have taken the branch, and therefore our value of K is now wrong. So now we have to go back and do that. However, if you design branch prediction properly, you'll guess it right approximately 95% of the time. So what happens is you get a 95% increase in performance where you're doing everything properly instead of having to insert these stalls before, with a trade-off of 5% of the time you have to go back and fix it. So there are two different types of branch prediction, which I think that's the next TGO, which I'll expect you to know for an exam. Static and dynamic. So static uses the information that was gathered before the execution of the program. And so that's limited because, as you know from working with C, you can read in and type in values in real time, right? So you get value from the user, so you enter a number, user enters 7, that affects the whole execution. If it's only being run and you have all the numbers done before the execution stage, then static branch prediction is very useful because you can actually use that to properly predict the branches. But in other cases, and other cases of 98% of the time, because you want the user to be able to enter information, you're going to be dealing with this concept of dynamic branch prediction, which uses information about the taken or not taken branches gathered at runtime to predict the outcome of the branch. So what's going to happen is when we talk about 2-bit branch prediction, these buffers, we're going to be actually using the previous prediction to try to use that to guess the next prediction. And we're going to use a finite state machine to do so. So what we're going to be talking about next is this concept of 2-bit branch prediction. So it maintains a branch prediction buffer. So kind of like, you remember out in pipelining, we have these buffers in between each stage. We have these buffers in between each stage to store information until the next clock. So here what we're going to do in 2-bit branch prediction is we're going to maintain a branch prediction buffer. And here in the definition, we call it a branch history table, recording its last behavior of the branch. So we're going to have these 2 bits that indicate what we're going to be actually doing, the next stage. So the small memory buffer is indexed by the 2 least significant bits of the branch instructions address. So you have your MIPS address, right? And so what's going to happen is you have your opcode, your RS, your RT, and your 16-bit instruction, right? So what's going to happen is the address of that instruction that you're going to get from instruction number, you're going to take those 2 least significant bits and you use that to do branch prediction. And if it's branch taken, if it's 1, 1, or 1, 0, that means we're going to predict the taken and we're going to go that branch. And if it's not taken, we're going to do 0, 1, and 0, 0. And we get to the finite state. So the common question is, well, if we have 1-bit branch prediction, right? Why aren't we just using 1 and 0 to differentiate? Well, you'll see how using this concept of hysteresis and making a more robust finite state machine will allow a more accurate prediction model. Because before that, what happens is if you have a 1-bit branch prediction approach, you're just going to be saying predict, 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 and then the moment you guess wrong, you're going to move to non-prediction, and then there's more opportunity for going back and forth in the finite state machine. Ideally, what you want to do is you want to stay in the same state as much as possible. I mean, same guess as much as possible. So what happens is there's two states that represent prediction taken and two that represent not taken. We'll be going over that finite state machine here on the next page. But the whole idea is that first you're going to have this, come on, there you go, have this taken, right? And so if you guess wrong, you go to this, that would be 1, 1. If you guess wrong, you're going to go to 1, 0. And if you guess wrong twice, you're going to go down to 0, 0, right? So 0, 1, if you guess wrong here, go that way. I should. So what's going to happen is you guess wrong, you go to taken again. If you guess right, you go back to the very strong taken. If you guess twice wrong in a row, then you go into the not taken portion of the finite state machine. And then if you guess wrong, if you guess correctly, you go to the stronger one. So what that allows us to do is it allows you to take two stages where you're actually guessing, predict, taken, predict, not taken in a row. So here's the general idea of it. So you have the least significant bits here. So what happens is it's 0, 0, so it's going to predict not taken. And so here, the instruction address, and here that's, we have 1, 2, 3, 4, 5, 6, 7, 8. So that's a 32-bit instruction. So 3C is going to end with hex 3C, therefore it ends with a 0, 0. So what's going to happen is now you're familiar. This is where you can take advantage of byte addressing. So here we have byte addressing, where two of these represent a byte, right? So 3C is a byte. So you can take the byte, that last byte here. So you have an instruction, and you read the last byte, and then you go, okay, well, I got 0, 0. I know in a pipeline multiprocessor data path that I can do predict not taken here. So instead of having to read the whole instruction, you can just read that last block. So it reduces the amount of instruction overhead that you have to read on it. And so this concept of taking this previous information here, predict taken, predict not taken, and using this last information is known as hysteresis. And the idea of hysteresis is that you not only use the current information of the program, but you're using previous information. So in that case, it's dependent of the system not only on its current environment, but on its past environment. So we formally define it, dependence of a system, not only on its current, it's the exact same word thing. So basically the whole idea is that not only do you know where you were, right? But you're using this finite state machine here. And so the last exam type problem will be combination. I'll ask you to draw the finite state machine. I'll give you a set of branch predictions and whether or not you actually did them or not. And you describe the state. So what you're doing is you start with predict taken, and we have, so this would be 1, 1, this is 1, 0, this is 0, 1, and this is 0, 0. So here it's taken star, taken, not taken, taken, and not taken. So what this means is you're predicting that it's not taken here, but here's what happens. We start this, let's say we start here, and we predict that we are going to take the branch. It turns out we're not supposed to. So we then go to this finite state machine. If we predict taken again and we find out we're not going to go to taken, we've guessed wrong twice in a row, so we go to this FSM. If we guess correctly next time that we're not supposed to take the branch, well, we just stay in the state. So what's going to happen is if we guess that we're supposed to
not take the branch, and it turns out we're supposed to take the branch, then we go to this state. And if we guess twice wrong, then now we realize that we should be taking the branch much more often. So then we go back to this state. So by using the hysteresis of the system and understanding what we did previously, you can optimize which branch you're supposed to take next. And so I'm going to scroll up because we have this example problem, 8.5. And so what the problem states is, given the 2-bit branch prediction method, so the exam will be draw the finite state machine, and then given this method, with the initial state of n star, right, and the following set of branches. And so what this problem states is these are what the actual branch is going to be. So we're going to have you're going to tell me what the set of branch predictions are. So you're going to have initial state. So if initial state is n star, are we going to predict taken, or are we going to predict not taken? We're going to predict not taken. Very good. So what's going to happen is if we're at n star state initially, right? And so we're going to predict not taken, and this first one is actually n, right? So that means we're going to go in the next state to n star, right? Because we're just going to stay back here. So the next one is n star. Are we taking or not taking the branch? No. So you would write n star, and guess what? To n, and then n star is the next state. So when you're on the exam, you'll be given this row, the actual, and the initial state, and you'll be filling in the rest of the table. And so we're at n star. Do we predict taken or not taken? No. For an n star, do we predict taken or not taken? No, we predict not taken. But the third part here corresponds to this. So that means we find out, this is a situation where we predict not taken, and then we find out that we were actually supposed to take the branch, right? So where do we move to on the FSM? To the left. So that is why here on our solution, this next state is n star t, because we're now in this state, right? So fourth state, we're in n star t. Do we predict taken or not taken? Not taken, which is why there's an n here. But we find out that our fourth value is t. So it turns out we're wrong again. So what state do we go to? T star. Very good. So we follow along here to T star. And now that is why this one is T star. So here, do we predict taken or not taken? Taken. And it turns out we were wrong, so we move to what state? T star n. Very good. So we're at T star n, taken or not taken? Taken. Very good. And turns out we were at n. So we move to n star. N star, taken or not taken? Turns out it's true, so where do we move to? N star t. And we're at n star t. We have n. What does that mean? It means we don't take it and we were correct, which means we go to what state? N star. N star. Very good. So that is your solution. So does anybody have any questions about branch prediction? So the PDF doesn't scroll down anymore. So what do you think that means?
Next section.
Now we've reached the end of the course materials.
Out of class already?
No. You're funny. No. Okay, so a couple things I want to go over. First of all, there's
this is the next lecture, which will be the Tuesday after Thanksgiving, is your final exam. Thursday will be the pizza party. So first thing I want to do is I want to do an exam review. So section 7 and 8 are what's going to be covered on the exam. Everything from single cycle data path through pipelining through everything we covered in section 8. So what do you think will be on the exam?
Reduce MIPS data path.
Reduce MIPS data path, yep.
Branch prediction.
Branch prediction will be on there.
Tomasulo's algorithm.
There'll be a Tomasulo's algorithm problem.
Pipeline.
What specifically about pipelining?
Hazards.
Yeah, I'm going to say, what is a pipeline hazard, and tell me the 3 types of pipeline hazards.
Data hazard, control, structure.
Data or structural control, very good.
Speed up with pipeline.
Yep, so you give you a set of 4 instructions, right? And first you tell me where all the hazards are. The second you tell me how many stages it would take if we did not have data forwarding. And the third one is what happens when we do have data forwarding, right? We're going to have that. So what else could we have?
The speed of between forwarding and not forwarding.
All right, well, I mean, that's kind of inherent in the problem. So. What are some of the other definition type problems that I've asked you to?
Multiprocessor?
Yeah, what specifically a multiprocessor? What are the? Yeah, TLP versus ILP. What was the other than this knowing this? What about branch prediction? Did I want you to know from
Static and dynamic.
knowing the difference between static and dynamic branch prediction? Very good. What other definitions? On your last quiz, what were the 3 questions that I asked?
That was a reduced MIPS data.
That was one of them. Truth table. And what's the other one?
Speed up computation.
Speed of computation of pipeline versus. Okay, that's what you're talking about. I understand what you mean now. So yeah, the theoretical speed up of pipeline over. So when I ask that question, what are the 2 things that I'm asking for? I'm asking for the ratio between. This is the one you got right, so mostly right. So it's the ratio of the throughput of pipeline versus the throughput of single cycle, right? And so what was the other thing that a lot of you left off that I wanted?
When it goes to infinity.
Correct. As n goes to infinity, it's going to get closer and closer to the number of stages, which is k. So what else? What other big problem did I ask about? Having to do with pipelining. So I did Tomasulo, but right before that I did something else. An example of ILP. I think it was on the homework I handed back today. It was delinquent, didn't show up.
It's going to be one about Snoopy Bugs.
Example 8.2, yes. Yeah. So you have 4 stage, and you should have some sort of number of adders, and you have to tell me how many stages how many cycles it takes to perform the addition. So is the problem any harder if I say it's 100 additions versus 20? Why not? It's the same pattern, right? So basically the difference is you figure out it adds the first 8, and then it's going to bring back the sum, and it's going to add A8, which is, since it starts at A0 in the way I presented it in class. You don't have to write it that way as long as you get the all 20 through, or all 100 through, or all 50 through, or however many. So you figure out how many times it takes to get to the next route through, and then you just say, all right, well, it took us up to 8, and I need to get to, I need to get the 100th integer, so I just add 92 to however many cycles that is, right? And then from there, you just do the one lap through, and then we have to add in the 2 stalls before you get the 2 other sums through. And then
that's the completion of the problem. I think there's one last definition I had on there that I wanted you to know. I wanted you to know about what happens when we have a stall. Or that one that I started that had to do with the what you do with the ERC, the error register, error program counter. Sure, I think there's anything else. I think that's it. CLP versus ILP. Yeah, that appears to be it. So that will be a week from Tuesday. And then Thursday will be the pizza party, and I'll hand back your exams and basically tell what you guys need to do on your final project and to get a good grade. The other thing I wanted to show you guys, so this is my little Excel spreadsheet. Let's see if I can zoom in here. I don't need Epic Pen. View, zoom. Yeah, that should do it. Okay, so course comparison. So I've gone through and talked about all the things that we covered so far this semester, and I've compared it to the equivalent courses at Mississippi State. So your ELE 385, their equivalent is ECE 4713. It's also listed as a grant course. At University of South Florida, my alma mater, CDA 4205. At Massachusetts Institute of Technology, 6.004. And University of Maryland, College Park, it's CMSC 411. So I've gone through and talked about what was covered in specific courses, and just to show you the comparison of what are the, quote, the higher level courses, or how it's offered throughout the country. So as you can see here, we went over K-maps and race conditions, combinational logic gates, sequential logic, finite state machines, stored program concept, that's load word and store word, as I'm sure you know that now. RISC versus CISC, not really discussed here. Computing performance. We also talked about, Amdahl's law, Gasky and Kahn charts, so talking about synthesis and all the different levels from a digital system. We talked about Shannon expansion for multiplexers and how to use that. We talked about fixed length encoding, so 32 MIPS data path. We didn't really have the time. We did go briefly into variable length encoding, talking about what happens when you have CISC, right? So you'd have 128, and it may not necessarily take up the entire instruction. Error checking, especially on your projects, you've done that in a tremendous amount of detail. I did not cover voltages and wires because you'll start covering that at the end of which course is it? 482. So 482 and 485, we'll be going over that. So if you also take my CMOS, you'll go into that course as much more than you go onto buffers and try finite state machines. Again, 482 and 485, we cover that in tremendous detail. That's covered there at MIT and a little bit at College Park. So coding standards, we went over the IEEE standards and motivations and modeling. I thought that really hasn't been covered anywhere, so I wanted to give you guys perspective on that. Combination basics, you'll notice that USF and Mississippi State don't really cover this at all. Timing and debugging, multiplexers, coder and decoder, latches and flip-flops, memory elements, and reading to and from files. And arithmetic logic units. So adders and subtractors, the only thing that I left out, Mississippi State, they cover floating point multiplication in lieu of covering some of this background work. I cut that out kind of for time because you did go over restoring and non-restoring division. Sequential and finite state machines, Mealy and Moore, talked about those, state transition diagrams, synchronous versus asynchronous. Metastability, so that's Q and Q not timing, latches and flip-flops, state minimization, and binary gray and one-hot encoding. Locality, you can see it's pretty much covered everywhere. You'll be covering that in CSCI, in organization, computer organization, that course that you have to take. So I left that out here. Improving cache throughput and write through and write back. For processor, constructing a data path, data controller memory, Register transfer language, that's really, in my view, very undercovered. They kind of just say, look at the MIP screen sheet, whereas I think that you should have a thorough understanding of how it's working. So to assembly. Also, everything with function pointers, function and return registers, that's not taught anywhere. So everything going over how do you call functions, how do you do pointers. That was kind of you guys were my grand experiment in seeing how well that would be picked up, and I can say that you guys did very well. When compared to doing the C to MIPS problem from last year's when we had done it in VHDL, your scores were a lot higher on that. So you guys showed a lot of understanding. In fact, I was kind of surprised that when I was talking to Patterson last week, the guy who people wrote your textbooks, I thought about C and how we're doing this, and he's actually going to try to adopt that into how he teaches the course. So he's like, oh, well, you've been doing this my whole life, literally. Loop implementations done by everybody. Interrupts, pipeline hazards, cache coherence. MIT does this one lecture on Turing machines. I left that out. But basically, you can Google Turing machine and learn exactly what they learned. And data forwarding, of course. So virtual memory, we covered everything that there is to cover about address, page tables, page mapping, arithmetic, context switching, TLBs, disk storage, and handling page faults. I/O, I left semaphores, bounded buffer, and deadlock out just because in order to take the MIT course, you have to have operating systems as the prerequisite. It is not a prerequisite here, so I felt throwing that concept at you guys before you take operating systems would have just been unfair. But other than that, and you can store to a disk. Congratulations. So multiprocessing, we went quite a bit into multiprocessing over the last couple of weeks. It's left off here. MIT was covered a little bit at Mississippi State, though they don't really go into course-defined multi-threading. We also talk about how that ties into cache coherence, Snoopy directory-based protocols, distributed memory, and did I actually teach you guys superscalar pipelining? Okay, so short version, superscalar, super pipelining. You know how you have 5 stages, and you know how you can improve throughput with K? Actually, I have taught you. So basically, if you try to make this number of stages go up, theoretically, that improves your overall speed up, right? That's called super pipelining. Congratulations, you've learned it. All right, so that's... And node networks, if I had another week, I would have gone into node networks, but basically it's how do you have multiple processors communicate with each other, especially basically butterfly networks, things like that. I just didn't really have the time. But the reason we didn't have the time is because we covered all this, which I think is much more important in an advanced digital systems course. Contemporary issues, power, future implementation, and pipelining issues, pretty much covered everywhere. Coding projects. So you didn't really have to do anything with you did memory blocks, like Turing machine or HSpice. You can do that in 482 and 485. The final projects, USF doesn't have one. MIT, they do theirs in VHDL, and so does Maryland. Mississippi State does a MIPS simulator, and you guys will probably hate me when I say this initially. It really, like for the arithmetic logic unit, they take in 2 integers to go, return A plus B if control signal equals 6, something stupid like that. It's incredibly, much more simpler than what you guys have done. However, the reason why I don't think that's an appropriate project for an advanced digital systems course or for this type of course in general is because it's still doing A plus B still disassociates what is actually happening at the digital level, right? So A plus B, well, congratulations, you knew how to add in kindergarten, right? Because you're not learning anything new. Whereas with you guys, you designed an AND gate, OR gate, XOR gate, then you made an adder, then you optimized the adder, and you put it into the ALU, you made a comparator, you did OR gates and NOR gates, you did a multiplexer, and you made your freaking ALU. And here's the thing, if you were to take this into a cadence synthesizer, guess which one would be smaller?
yours because you designed it precisely how it should be done, whereas if they have to rely on the design automation tool, which is not necessarily going to be as effective. In fact, typically when the more you rely on the design automation tool, the more bloat you get. So that's the reason I did it, because that will make you better engineers if this is the job type that you'll pursue. So in my view, you guys covered quite a bit of material this semester. I would say you performed as well as the MIT kids or all these other schools that are allegedly much better than Ole Miss people. You know what I'm saying? Like, so if there's one thing that you've learned from me, it's this. I pushed you guys hard. I asked a lot from my students, but I want you guys to know that at least for one semester, starting this semester, you guys were the elite people in the world at this, right? Nobody can take that from you. Anytime somebody says, oh, you're from Mississippi or you're just this or you're just that, remember, the best computer engineering class in terms of advanced digital systems, not at MIT, it's not at Stanford, it's not at Cal Berkeley, it's you guys. You're the best. And no one will ever take that from you. If you learn that from me, do not ever let people tear you down on that, right? And you know that you have the potential to do it. That having been said, I do have one last quiz I want to give. It's a one problem quiz, and when you're done with it, I described these four instruction. Describe to me the pipeline hazards, overcoming the hazards, and what happens when you insert data forwarding. Hint, it was literally the exact same problem from your homework. So I hope you guys were over that a little bit. That was a few homeworks ago, right? Xavier's like, oh no.